Hello, everyone, and this is yet third part of the heart. This section is more about flow, and you get me with my hat on because I just came back from playing tennis. So here we are. This section we're going to talk about fluid mechanics, the cardiac cycle, and cardiac output. Really important concepts. So here we go. So when we first think of blood flow, think of this. Each half of the heart is going to pump about 2.5 million liters of blood in a year. This little muscle that you have is just going to be continuously pumping the approximate 5 liters of blood that you have, and it's constant, right? So that doesn't help you to know how much you pump in a year. You'd like to know more about what about per beat and per ventricle, right? How much is every side of the heart pumping when there's one particular pump? Well, that value of pumping one side when that squeeze happens is called stroke volume. Okay, the volume per one stroke. And we're not adding both sides, but we're adding each individual side. So how much is that? It's about 70 milliliters. And that's the approximate for the left ventricle. So we're thinking more about the left ventricle because you're thinking of it sending blood to the rest of the body, correct? So here I've drawn a line through this, and you would have a stroke volume for the right side of the heart, a stroke volume for the left side of the heart as they pump simultaneously, and out comes this blood. So mostly we want to know medical values always in per minute, right? You get your respiratory rate per minute. You want to know what this is pumping per minute. So we make that conversion always. So blood flow rate is going to be in volume, how much of it is pumped, the volume of it per minute. That's cardiac output. So cardiac output, 5 liters per minute at rest. And if you need it in gallons, so about 1.3 gallons. So that's the total blood volume pumped per minute, cardiac output. So let's go back a little bit. Stroke volume was the stroke that you did of each one as you pumped each side, right? But when we're going to convert it, we want to know what that volume is exiting the heart as cardiac output, which is the total amount on both sides. This measures the effectiveness of the heart as a pump. So if you get a value of cardiac output, you're looking at, are we pumping enough? Is this heart that's effective, or is it under pumping, or what's happening? Okay, so the cardiac output, let me see if I can get myself out of here. Cardiac output has a formula, and that formula would be your heart rate times the stroke volume. So that makes sense, right? Stroke volume is how much each side is going to eject, and then you want to know how many times you do that if you're converting it to a minute. So you have beats per minute, which is heart rate, and mLs per beat, when you're talking about stroke volume, and the beats would cancel out, and you end up with a value that's in milliliters per minute. That's what you want to know, effectiveness of the heart, milliliters per minute. How much is it pumping? So I give you an example here. This is for an individual. This is Sonia Mendoza, and her heart rate is, let's say, 75 beats per minute. She has a stroke volume of 68 mLs per beat, and you would know this through sonograms. They could figure out how much of it is ejecting. So you're multiplying the 75 times the 68, and it's going to give you about 5,100 milliliters per minute, 1,000 milliliters per liter. So you're going to convert that to liters, and it's about 5.1 liters that this individual is ejecting out of both sides of the heart. So in this clicker, like your questions that you're going to have later on, the stroke volume is, I'm going to let you do these. I'm not going to solve it for you. You should do these by yourself. Okay, so a slight change here. What is pressure? Pressure, blood pressure, you can say, oh, it's 120/80. No, define it? Define pressure. So defined pressure in a fluid. It's the force exerted by that fluid on its container. So if it's crashing along the walls of a bucket, it could be right? That's pressure. If it's crashing inside a ventricle, that's pressure. If it's crashing inside an aorta, that's the pressure exerted by this fluid on its container. And so this, I'm explaining the force exerted by blood on the vessels, right? And if the fluid is moving, which it is in your blood, right? It's going to be moving, then the pressure drops with distance due to friction. See if that makes sense. If you have a big long tube and along it comes this fluid, the pressure at the beginning of that tube is going to be different from the pressure at the other end of the tube because it's drag along there. There's friction as it goes along that container, and it's going to drop. Also, fluid tend to move if the pressure is the same on both sides. You're going to have always fluid moving from high pressure to a lower pressure. So dropping pressure over distance keeps the blood moving. That makes sense. And that moving blood we're going to call flow. Flow. So that change in pressure over distance is going to produce a pressure gradient. We've talked about gradients before, or a flow. Without that difference in pressure, it would stop flowing. So in this diagram, I tried to draw, hopefully successfully, big fat arrow here. This fat arrow is getting smaller and smaller and smaller as it goes, as the pressure is dropping, but it's what's keeping it moving because the pressure is higher on one end and lower on the other. So in the entire body, you have to think of where is pressure greatest, right? You've just ejected the heart, you've squeezed. The highest pressure is going to be at the aorta, right when it's coming out into the aortic arch. And where is it going to be lowest? Well, then it's going to go through arteries, big arteries, arterioles, smaller, smaller, finally tiny, and then into the venous, larger veins, and little veins into bigger veins. And you can imagine what that's doing to the pressure. The pressure's been dropping all the time. So by the time it gets to the vena cava, that pressure is not 120/80. Much lower. Much lower. How much lower? So this is the interesting thing that always blows me away. Here is the mean systemic blood pressure. We have it up in the 90s here in the aorta because let's say that that's what it was in the aorta. Let's just keep it simple that way. And if it's at 93 millimeters of mercury in the aorta and it's dropping in the arteries, right? And then it's going into little tiny arteries. It's dropping more. Now it's coming into capillaries. It's really dropping. Oh my gosh, look where we are already. At 30. We started out at 90. And now we keep going into little veins. Now where are we? Like at 15? And then by the time it gets to the vena cava, by the time it's coming into my right atrium, it's so low. It's like 2 to 5 millimeters of mercury. So low. It's a miracle it makes it there, but it does. So pressure is greatest at the aorta, lowest at the vena cava. Now, a little bit more about this flow that's going on in this tube here, okay? And I've told you that it's only going to flow if there's a positive pressure gradient, if there's a difference, right? So it needs to be higher at one end and lower at the other end, and then you're going to get flow. Flow is going to happen with that difference in pressure. Pressure gradient. Usually delta P is what's signifying a gradient, a pressure gradient. And so I really like this diagram because this is the drinking a milkshake out of a straw is the really nice example of what's happening in your blood and with the vessels, right? You're trying to move fluid in through your vessels. And a lot of things are going to matter. How successful you are at that, how successful you are at drinking out of your straw. What would you need? Well, this kid needs to put pressure on this, right? Suction pressure. And without suction pressure, it's not going to come up the straw. What else is going to matter? How thick the milkshake is. If it's really thick, it's going to be a whole lot harder to get flow. If the straw is tiny, if it's one of those stirrer straws from coffee, it's going to be really hard. So there's all these variables that are going to affect flow. And that's the same in the body, right? Because there's resistance to flow. So that resistance is friction along the straw, the little straw that could be wide if it's a boba straw, it's going to be a whole lot wider. So we think about peripheral resistance, and that's resistance in the vessels. So you could have more resistance or less resistance in those vessels if you, for example, had atherosclerosis. If you have atherosclerosis, there's going to be narrowing of those vessels. If they're narrowed, it's like the analogy of the straw. The straw is too narrow, and it's going to take a whole lot more force to get that blood to where you want it to. That resistance is going to be increased, and the heart's going to have to work a lot harder. So that resistance is going to be determined by viscosity. Oh yeah. How viscous, how thick that milkshake is, or how viscous, how thick that blood is. If you're dehydrated, it's going to be thicker. If you're not dehydrated, it's going to flow more easily. Vessel length. What about the straw? If you have a shortish straw, that's fine. What if your straw was 4 feet? It's going to be a whole lot harder to get that milkshake, right? Vessel length doesn't change in individuals, only when you're growing, right? You have a smaller length of that vessel and then larger, but it is a variable that in this situation, in physics, it matters. It's not going to matter so much in the body. But what about vessel radius? Vessel radius is gigantically important, right? If you have the narrowing of that vessel, it's going to be so much harder to get fluid in through that straw. If it's broader, it's going to be so much easier. Actually, the resistance here in a formula is here of the viscosity times the length divided by radius to the 4th power. And this is just the physics of it, right? You don't have to know how to y of the 4th. It's just this is how it behaves. So any little change in radius is going to give you a huge change in resistance. So the body is able to change that. It's able to vasoconstrict vessels, and it's able to vasodilate vessels and allow more blood flow to travel. So that's really going to be the variable that's the most important variable in this formula. Just to look at this a little more closely, if you had a barrel like this and you had a radius of 1, you'd get a certain amount of flow. If you had a radius of 2, which is only double, you would get a lot more flow. How much more flow? 16 times more flow. Just because the radius of this has such a huge influence on what volume is going to exit through that. Okay, this last slide is in terms of resistance, and this slide is in terms of flow, which is relative to 1 over the resistance. So what you really have to remember here is that when you double a radius, which is unusual in the body, you're not doubling the size. You're just increasing it a little bit or decreasing it a little bit. You're going to be changing the flow miraculously. It's going to change so much, much more so than the viscosity of the blood or the length of this vessel. So think of radius as the most important variable. Okay, so I'm going to stop at this equation, which is called Poiseuille's equation, really important, where it's going to integrate radius, pressure, like the pressure of the suction pressure. Here it's the pressure of the heart actually moving that fluid, and then the length and the viscosity. So let's stop here and I'll continue on the next video. Thanks, guys.